I'm going to start us off sort of with a quick facility level overview. And I just wanted to give you guys an idea of what we're going to cover or what we expect you to already know. So we'll talk about how to log into our systems, how to set up a usable environment, how to use the job scheduler, use interactive nodes to debug code, or submit jobs with job scripts. And we will be using the tutorial that's down here in the Polaris directory for now. And there should be soon some coming for Sophia and Crux, which are new systems that we're deploying, and eventually Aurora. So if you haven't already gone, I've copied this URL into the chat. So feel free to go and follow along there. And of course, you can use this later also to do this yourself if you haven't already logged in. So through this tutorial, I'm going to assume that you know how to use GitHub, you know how to use Git repositories, you know how to use SSH. You're not a computing beginner. You are someone who has used software on a cluster of some sort, using a batch scheduler, that sort of thing. You know how to get around a Linux terminal. This isn't intended to be a tutorial from the ground up. It's intended to bring someone who knows how to do computing and help them familiarize themselves on our system. So I'll start with this ALCF system overview. And we have these different networks that we've set up in ALCF. We sort of have our primary production network, which is where Aurora and Polaris are living, and Sophia. And that's also where Crux will be stood up. Aurora is the big machine, the exascale machine that is currently being commissioned and prepped for users to begin running science on the 60,000 GPUs, the 10,000 nodes that we have there. Polaris is our current production machine, which has about 500 nodes for production Nsight work. It has AMD CPUs and NVIDIA GPUs versus Aurora, which is all Intel. Sophia just came online. Access can be requested through our discretionary allocation form, which I can show at some point. But that's 24 DGX nodes. This was previously part of Theta as Theta GPU, and has now, since Theta, all the KNLs were decommissioned, we spun this off as a separate, really intended to be a Jupyter notebook geared system where people can do lightweight data analysis or visualization tasks. And then we have our storage architectures. We have, when you log in, of course, you land in your home directory, just like any other Linux system. The home directory is a separate, smaller file system, which isn't really intended for use during production on the system. So if you are going to be installing big software frameworks, I would recommend you use our production storage system, Eagle, which is a 100 petabyte system. This is much bigger, right? Order, factor 1,000 bigger than the home directory, and it's intended to be more performant on the compute nodes. So when you're running jobs on Polaris, you're going to get better performance with software or data sitting in Eagle than you are in the home directory. And then we have these other two network enclaves, as they're called. One for the AI testbeds. So these all sit in a separate network enclave. They have their separate storage that's available. And those, again, can be requested through discretionary requests. If you search ALCF discretionary, you will find the form. I can bring that up at some point. And in the future, we're going to have a low security network enclave, and this is where we're going to be doing a bunch of education outreach. And the idea of this one is that we don't have to go through all the security hurdles that you need to get on these systems. So we can get, students on here much easier without all the paperwork. At least that's the goal. So hopefully we get there. So hopefully you sort of know what a supercomputer is, but in general, a computing node, one node of any supercomputer is kind of looks like a standard computer, right? You've got a CPU, you might have a GPU, you have a motherboard that connects those all together with some memory, and you have some storage. Now, in a supercomputer, you've got many of these in a small form factor that you can just slide into racks and racks and racks. And the thing that makes it super is the high-speed network. So a standard university cluster, for instance, might have a very nice but still slow Ethernet connection that connects all the computing nodes together. It really wasn't designed for the nodes to be treated as a large set of machines that can do efficient calculations together as a unit. And so with a supercomputer, the idea is that you can run thousands of nodes all doing the same computation and get very good performance. So you don't get a lot of slowdown as compared to doing work just on a single node. So that's sort of the big difference. And supercomputers are big. This is ALCF staff in front of Mira, which is a supercomputer we decommissioned a few years ago. So that's just a quick introduction. I see a Q&A popped up. What was that?
They were asking about the differences between different Eagle or Grand or the other file systems. And I also asked to put questions in the chat other than the Q&A.
That's fine. Eagle and Grand were meant to be relatively identical, with Eagle being intended for a external facing data service. So in principle, if we have users who are processing large data sets for a community of users, they could stage their data in Eagle and make it available outside ALCF. Grand was intended for internal, although portions of Grand have been subsumed into usage for Aurora, which is why I would say just stick with Eagle for the moment. Grand is still available on Polaris, but okay. So then we will move down into Polaris specific. So again, I'm going to assume that you have some basic Linux terminal usage capabilities, some basic cluster scheduling usage, and then you know how to write and compile code. This isn't a software tutorial. So really here in this session, I want you to get an idea of how to set up an environment on Polaris using our module environment manager. So here you can see a picture of Polaris on the data center floor. I give you an idea of what's inside the racks here. So you can see the nodes stacked up and a description of the nodes. So the system is a total of 44 petaflops. Each node has 4 NVIDIA GPUs and an EPYC CPU with a total of about 560 nodes, although 60 of those nodes are dedicated to APS real-time processing. So roughly 400 for production science. When I say production, I mean things like people who have science allocations on our machine. whereas APS is being handled in a different special method. And so, of course, when you want to log in, you need your ALCF username at Polaris, and you can SSH into our machine. It's going to ask you for your password, which comes from either your mobile pass app on your phone or the little dongle that they give you with the keychain attached to it. Which I don't, mine's in my desk. I haven't used it in a long time since the mobile app. So once you get there, you will be sitting in your home directory. My home directory is probably quite a bit messier than yours. And I've already checked out the repo, so you can clone this GitHub into your home directory. We're not going to be doing any super performant coding here, so I'm not worried about people using their home directory for running software on the system in this case. But like I said, if you're doing performance oriented computing, you really want to use the project space that you're given with your allocation. So, yeah, so log in. Let's talk about the file systems for a moment. So like I said, we have our home directory. So here's my home directory. And then if I look at the base, the root file system, you can see Eagle and Grand are listed there. And they just point to the project spaces on Eagle and Grand. So when you get an allocation on our systems, you'll get a project directory or a project name. And that will be not only translate into a folder under here, but it will translate into a user group. So if I type groups, I can see all the user groups I'm a part of. And a lot of these stem from project spaces that I'm members of. So you'll probably have a much smaller list, but I can usually take one of these and explicitly do an ls down here to find one of these corresponds to a directory. But if I just do an ls there, you'll see there are lots of project directories because of course we have quite a few users. And you'll notice there's an ALCF training one as well. So we even have a project space for people doing work. And everybody should be a member of this group, the ALCF training group. And so you'll be able to use this space for testing during our reservation today. Okay, so that's a quick look at the file systems. So if you clone the repo, there's some helpful example code in there that we'll look at in a moment. The main thing for this page, for this, this is the README in here. The main thing is to get familiar with this environment modules thing, and this is a link to the main modules documentation page, but I'll give you a quick intro here. And we'll just do it like this. So if I do, going to be confusing with that one down there, so I'm going to move that off screen. If I do a module list, this is going to tell me what modules are currently loaded in my environment. And you can see it's a lot of system stuff. Like there's some Cray, PE is typically programming environment. You can see Cray MPitch, which is the MPI library. PALS has to do with job scheduling. libfabric has to do with the network. You can see there's an NVIDIA HPC environment that's loaded here. This is part of this as well. These PRG-ENVs are programming environments that are intended to be packaged together, lots of these modules. So when you change this, A lot of these might get swapped out and replaced with something different. And we'll talk about that in just a moment. Another important one is module avail. So module avail shows you all the modules that you have available to you. And they're organized by directory. So module takes a look at your module path environment variable. Maybe no underscore. Yeah, there we go. Which will be set by default when you log into something. Let me repost my, oops. Let me repost this for people who arrived late. Okay. So when I type module avail, it means available, which modules are available. It's going to go through each of the paths that are in here, and it's going to look for configuration files, module files. And it's going to list all of them that are available. Now, as a new user, so I've added this to my bash RC. But many of the modules that we're going to look at have module files that live down here. And we want to tell module to go search in that directory and tell us what modules are available there. And you can do that by using module use and then adding the path. And I will mention that later. Oh yeah, here. Where we want to use this module path. And of course, I've already done this because I've added it to my bash RC. So anytime I log in, it does that. And so when you do module avail, it will go through those directories and it will list all the modules. And so you can see in that module file directory that I posted, you can get various CUDA toolkits. So these are the CUDA drivers. If you want to control, right, I mean, there is a CUDA driver or CUDA toolkit loaded by default in that preloaded module, right? The PRG NVHPC comes with a driver. But if you want to control which version that you have, I don't remember what the default is, you would want to load up one of these by hand. And you can see there's quite a few modules in here, including some SPAC installations. If you're familiar with SPAC, there's some Cocos installations. If you're familiar with Cocos, you can see LLVM, Conda, which we'll talk about explicitly here, cuDNN, Forge, HPC Toolkit, JAX, some visualization software, Tau. So a lot of these we will touch on, but you can see as I scroll through here, there are a lot of other system packages. So these are all coming from Cray HPE. And if they have this L, that means they're loaded. If they have a D, that means they're the default. So in this case, for instance, if I say module load cuDNN, it's going to automatically choose this version and load it for me. Or I can explicitly module load cuDNN / this. So, and we got more documentation on this on our website. This is meant to really be a quick crash course. Okay, so I think the next step would be showing you how to load. Yeah. So like I said, we can try loading our modules. And really when we load, it's just adjusting our environment. So it's changing path and LD library path and maybe some other things, right? Like CMake prefix path or something like this, where it's trying to tell are tools that we're using, where to find these new libraries that we want to use. So it's adjusting your environment. So if I do, let's see, echo LD library path, you can see what it looks like there. But if I do module load, and let's just do this, let's load up this standalone toolkit. And now if I do it again, so you'll see there's been a path added to the libraries. I'm sure my path probably also points to the binaries, right? So if I look down here, you'll find all the tools you'll need for CUDA compilation. There's also like I said, these programming environments. The default that's loaded is this NVHPC environment, which uses all the NVIDIA compilers, so NVC++ and for when you're compiling. And if you want to swap that out with say just a vanilla GNU environment, you can do that. So if I say, let's see if this works, module avail prgenv. So this should show me all the environments or all the modules that have this string inside, but these are the ones I'm really interested in. So we can swap between these four and it will adjust our environment. So first I'm going to unload the CUDA driver that I loaded. And now let's see if we can, let's swap this. So I think it's actually, is it switch, I think is what they use. So switch, and I'm going to get rid of the NVCC and let's switch to a GNU. Okay. So if I look, you can see my LD library path has changed quite a bit. Not sure if the path changes quite as much. But you can see when we did the echo back here, compared to now, there's quite a bit of difference here. Now, we'll talk about compilation, and that's where you really see the differences, because a lot of this applies to using the CRAHP wrapped compiler commands, which we'll touch on next. So we'll come back to this and get more details there. Another thing that you get using this soft module files area are these SPAC installations. Sure. I'm pretty sure swap, well, I don't think, let's see. Okay, so they are the same. Swap and switch are synonyms. Okay, so if I load, for instance, one of the SPAC modules, now that should, yeah, so when you load these, if you're not familiar with SPAC, SPAC is an HPC-oriented build environment where you can build an entire environment from the ground up, starting with compilers, and based on everything that you've built, you can then build other software. And it really makes sure that if you have an environment that you want to reproduce elsewhere, you can do that from the ground up. You know, bootstrapping off the system to build up your environment. So when I loaded this, a bunch of new modules became available to me. So you can see a new set of folders have appeared in my module, list of what's available. And you can see they come with quite a few additional tools, right? So things like HDF5, some new Cocos libraries, NetCDF. There are some Python modules that are available. And so there's the base. And in this case, I asked for the SPAC programming environment, GNU. There's also just base. I go back to my list up here. We'll see all the ones that are available. There's also an NVIDIA version. Okay. But you can see there's quite a few additional libraries available that you can use, including some custom GCCs or some different versions of GCC, which can be helpful if you have specific requirements for building. And so then after you've loaded the SPAC environment, you can module load any of these. Okay. And I should be able to do module unload to remove those and go back to the way I was, which you can see those SPAC modules have disappeared again. And so that's just removing the stuff from your environment that you previously had. Okay. And so now we go on to the next, which is talking about the scheduler. Okay. So here we're going to talk about how to use schedulers to execute tasks on the supercomputer, or we assume that you know how to use schedulers, sorry. And we assume that you know that a job defines how we run. So you have an application, you want to run it on a bunch of worker nodes. When you log into the system, you're not on a worker node, you're on a login node. And you can't run your application there because you share that node with all the other hundreds of people who are logging into the system. And so it would run really, really slow. So we'll talk about how to run an interactive job, how to submit a job, monitoring a job, and removing a job. Kind of expect everybody knows what a scheduler is. We use PBS. If you've been at NERSC, they use Slurm. Others, there are lots of different schedulers and configurations of schedulers that people can use. But I think generally most of them tend to name their commands similar, which is helpful. But the formatting of those commands can be very different. So that's where we'll try to highlight how to do those on our system. So let's start with running interactively. So interactively just means you log into Polaris, you're on a login node, right? You don't want to run your application there. But the first thing is you need to compile it, maybe do some debugging. And if you have some debugging task that you need to do that requires you to be in a quick debug loop, right? Where you say you have a seg fault and you run it, 2 seconds later, it's seg faults. Well, you don't want to submit a job, wait for it to sit in the debug queue for 5 minutes, for that to start, run 2 seconds, seg fault, and then you iterate. So an interactive job lets you, when the job launches, it automatically SSHs and puts you in a terminal on that worker node. So now you're on a compute node and you can run the job and watch it fail and interact with it and figure out why. That's why it's called the debug queue, which is what you'll see right here. The debug queue is explicitly intended for users to run short single node jobs for debugging, because all of our other queues require you to use at least 10 nodes. And if you want to run for the longest time, which is our 24 hours, you have to get much larger than that. Because we're a leadership computing facility. We encourage our users to go to large sizes. That's the goal. And of course, Polaris is also a tool that we're using to prepare for Aurora. So if you intend to be running on Aurora, ideally you should be at least capable of running on the 500 nodes of Polaris, because there's 10,000 nodes on Aurora. Okay, so the QSub command that we can run on the command line has quite a few different pieces. This -I is explicitly what we're telling QSub that we want an interactive job. That means that instead of passing an executable to QSub to execute when it starts the job, we don't want that. We want you to just start a shell that we can have an interactive debug session with. And then we need to tell it how many nodes that we want to use. So we'll use this -L select. And we need to tell it how long we need that. And you can see the formatting is in hours, minutes, and seconds. You can also go by days if for somehow that needs to be longer and you manage to get access to that. There are ways, but we tend to not allow people to run for more than 24 hours. And then you need to specify which queue are you submitting to and which file systems you need. And you can define multiple file systems. Typically, I would suggest I'll always just set this to home and Eagle, have your project space on Eagle, have your job or your software sitting in your project space in Eagle, and it should be launched from there. And then what's the project that you're going to charge against? Everybody who has access to our system has to have an allocation, either a discretionary allocation, which are really easy to get, and it's how we give people startup time. It's, we want you to be able to get access to our systems and learn how to use them. And then we want you to, learn how to use them at large scale so that you can submit a successful ALCC or Nsight proposal, where you're going to get large chunks of time. With a discretionary allocation, you can get, a couple thousand node hours of time, but it's not going to get much bigger than that. And they expire after 6 months. Whereas Nsight and ALCC can get you multi-year allocations that are millions of node hours big. So let's, here I'm just pointing out that we use module on the worker nodes too. So everything that's available on the login node via module is available on the compute nodes via module. So we'll go over that. So let's go ahead and do that. So, and point of doing that live as well, I'm going to first, with PBS, in these user tutorials, we typically always have a reservation. That means we have set aside nodes on Polaris for you guys to use. So please feel free to submit jobs while we're going along here. So I'm just going to set up a job for an interactive node, but you guys are going to need to know what queue to submit to and which project to charge against. So we can do that. This isn't in the documentation, I don't believe, at least not in here. I think I have it in the quick references down at the bottom. But if we type in PBS R stat, R stands for reservation. Stat is the status. I'm going to list all the reservations that are available right now. And we are this one right here. And so I can do PBS R stat -F, which is going to give me all the details of this reservation. So I included the reservation queue name, just so I didn't get all the details from all of them. And so you can see this is a reservation for this Polaris Bootcamp. Our queue is called this. You can see when it starts and ends. It ends at 2 o'clock today. We can see things like the number of nodes, so the node CT count. So there's 64 nodes available. And the authorized groups are ALCF training. So we can try and submit there. So this is also our project space. So I should be able to, I think I already submitted a job here. Let's check. Choose, there we go. So here's my interactive. Tell it which queue I want to submit to, which project, for how long. And I'm just going to say 60 minutes. I want one node. And oops, I didn't realize this was running off the screen. That was probably confusing. Okay, there we go. And then we specify the file system. And I'm just going to put home because all the testing stuff is right here in my home directory. And so that should bring me right up, unless all of you guys have very quickly taken all of our nodes. There are only 64 that we have set aside. So now you can see I'm on an actual worker node, which has these very systematic names to them, which mean something to all of our operations people, but are unique to that specific queue, to that specific node. Now it's probably useful to notice or to know that I can start up another shell, SSH into Polaris. Need to make this bigger so you can see it. Okay. And once I'm over, so once I have that node, I can actually SSH directly into it. So I can have two shells on the worker node if I need to. And sometimes that's useful if you're running an application in one shell and you need to check the memory utilization or something like that in the other one. You can see what's going on the GPUs, stuff like that. Sometimes that's helpful to have two. So once you have the shell, or once you have the node, you can SSH into the node multiple times. Okay. The other thing that I wanted to point out, I'm going to exit that in the second shell, and I'm going to do a QStat. So QStat tells us the status of the queue, and it lists all the jobs that are queued or running, and a bunch of information about them. So I have to go all the way to the top here, and you can see there's job IDs, usernames, the queue names. There is an ability to set a job name if you like. There's session ID, number of nodes, a task ID, and then how much time was requested and the current state. And I'm a bit frustrated that PBS doesn't let you make this a long name, so you have to just know, like, H is held, like your job is held, which means it's not going to run. It got held for some reason. Either you held it or the system held it. Q means that the job is queued. It will run at some point. Let's see, can I find an R? There we go. So there's a running job. And there is how much time has it been running, right? So it tells you how long the job is running. You can see this one is a 12 or a 24-hour job. It's about to exit, and it's using 120 nodes. Okay, so there's a lot. This is a failed job. Okay, so it started up and very quickly failed. So there's a lot of information here, but if I do qstat -u parton, which is my username, I can just look at my job that's running. I can see it sitting here. I know which queue it's on, how long it's been running, what the state is. And so that's telling me about this job right here. And again, when I load up here, module list is what I wanted to do. Module list defaults to whatever the default is. And I need to make sure that if I have a certain setup that on my node, on my worker node, I set up that software as well. So if I needed to change my programming environment or which CUDA toolkit I'm using, all of that needs to happen here before I start, testing my code. I see a lot of comments going by. Hope everyone is getting their
Taylor,
answer. Yes.
can you put a command line one more time in the chat, the way you submit a job?
Yes. Right here.
And if someone believes they do have an active account, then let me know and I will make sure to add them. It will take about 10 minutes to become active, but I can do that. But I did go through all the names who were registered. And if you did not have an active account, I can add you. It's just only if you have an active account. Thank you.
So that's the command I used. And so once you're here, like I said, you need to set up your environment. And you can do things like NVIDIA SMI to see what the GPUs are doing. You can see we have 4 GPUs per node. They've got 40 gigs of RAM. Of course, I'm not running anything right now, so it doesn't report anything there. What else did I want to? Okay, so from there, we were going to go on to talking about submitting your first job. So are there any questions about the interactive jobs here?
I think one question was like, people notice when they do interactive jobs, if they set the modules beforehand and everything is back to default, which is true, you need to set it after you get the interactive session, or simply pull all of them in a script and just run the script. But that is the case. So
Yep.
for that too.
That's right. And so we'll go over that now with submitting a job. So I'm going to exit this. Okay. And we're going to go down into the Polaris directory. So we can submit our first job. There's this hello world. So something to note here. So we've got a bash script that we're going to use as an executable that we pass to QSub. Okay. Notice if all 64 nodes get filled up, we will, you'll sit on the queue, like you'll sit there and it'll wait for the job to start. Okay. And did I? So I'm going to go down here to the examples and we'll just take a look at this file real quick. Let's make sure that I have that set correctly. So because this, I think, is from last time. So I'm going to update that. Not that actually loading GCC there is important. That will just do, that was already loaded. We'll test with this. Okay. Okay, so instead of that, I'll just load this. So when you're making these job scripts, you can put the PBS, the QSub commands at the top if you prefix them with these. And the reason to do this is that a lot of the times you don't need to change those parameters. The nice thing is that if you need to change one of those parameters, you can still use the command line to override any of these. So if you set it on the command line, it will ignore the one that's here in the script. Now, I usually always want my log files to go out into a directory. So you can set where the output and the error log go. And I'm just going to output those to this logs directory. And then the project name needs to be changed to ALCF training. And the queue needs to be set to that number, which I'm going to cut and paste from the chat. And this super fast job, so I don't need 30 minutes. I'm just going to see if I can set this to 5. Okay. So this job will start up. It's going to load a custom CUDA toolkit, which we're going to quickly ignore because we don't need it. And then I'm going to set my number of GPUs per node, which is just an environment variable. I'm going to set that to 4 because that's how many they are. Then I'm going to run an MPI job that uses 4 total ranks and puts 4 ranks per node, processes per node, on each node. So this is just a single node job. And then it's just going to run echo hello world. So nothing too exciting. And so then I'm going to use qsub to submit this. And since all the command line parameters are defined in the shell script, I don't have to specify anything on the command line. How does the PPS? I would have to refresh my memory on Slurm. But I'm sure that there's probably I wonder if we have that in our documentation. Murat, maybe you can look that up real quick. See if we have that. Okay, so I submitted that job and it's already done. So I recommend making an alias in your bash script. I use qsme to be an alias for qstat-user. That way I don't have to keep typing it. And plus, most of the time I only want to see my jobs. I don't want to see everybody else's jobs. So that means the job is done. And if I look down in my log files, oops, I have some old ones there. You should go in order. So you can see today's the 17th. So let's see. If I look at this one, you can see, oh, okay, this one is unknown. And that's probably because I did not include the module use soft. I'm surprised it doesn't get, because it's not executing my bash RC when I log in, or when I run submitted job. So in reality, I should have done module use, soft module files. Try that again. But let's quickly look at this one. And you can see, despite the fact that the module didn't get loaded properly, it still printed hello world 4 times because it launched an MPI executable or MPI job with 4 ranks. And so other job finished. Let's make sure that error went away. Yep, there we go. so no error that time. So including that module use soft files was the key there. E, what does E? Actually, I said F is failed, but actually I think F is finished. E may be. Here, let me grab this. Actually, I'll just do this. I'm just going to commit. Yeah. I have to pull down some changes from. Okay, so if you get pull on that, you should get the updated hello world. Okay. Is everybody else getting there? I see some discussion about the file systems, which makes me think about the fact that be aware that if you submit a job that says you need a file system, if for whatever reason that file system goes down, so let's say on a day, for whatever reason, Eagle goes down, but Grand is still up. Your job, if you say you need Eagle, which is down, your job won't start until Eagle returns to an operational state. So just be aware of that. If you're like, why is my job not starting? Even though I don't need Eagle, right? And so that's, with the file systems, you should only include the ones that you need to run your job. Okay, so let's continue. Oh, it's useful to note that also your job script needs to be an executable, right? QSub explicitly expects an executable. And so it is important to know that you need those to be an executable. So that means you need to also tell it what it's going to run. You need that proper shebang if you're not familiar with the term. Okay, I'm going to try and, I don't know how to clear someone's drawings, annotate, clear all drawings. There we go. Okay, so we talked about monitoring your job. With QStat, and QStat-U gives you the your specific. There's also QDEL. So if you cut and paste this into here, you can delete your job. And then, of course, the standard out always falls into these job ID.erou. Okay. And like I said, I usually put my logs somewhere because otherwise, every time, especially if you're debugging and you're running a bunch of jobs, folder just gets full of stuff. And then I put a PBS cheat sheet down here that I think is useful. I think actually, I also have an alias for QStat. Yeah, so whenever I type QStat, I always include W and A, which is just giving me more information. So for instance, if I do which QStat, if I run the actual binary, this is the default output. which gives you the name, the user. Like, it doesn't include how many nodes were submitted, the wall time, how much time has elapsed. So that's why I added an alias that just anytime I type QStat, I automatically get the W and the A. Because that way I get all this additional information, which is helpful. So anyway, so you can see some interesting tips here. How to find out like what nodes are available, what's the status of the nodes. You can get the queue information. So if I do qstat-q, you can see all the queues we have available. Mostly what you're going to need are these three right here: debug, debug scaling, and prod. Prod is actually a routing queue, which you can see here. It routes to small, medium, and large based on how many nodes and wall time that you request. One of the annoying bugs of PBS, or well, I don't know if it's a bug, but if you submit a job to a queue, to a routing queue that doesn't fit into any of the queues that it routes to. So if you submit a job to prod that's a single node, your job does not fit on any of these queues because we don't allow you to run a production job with one node because we're a leadership machine. Your job will just disappear from the queue. And we are trying to find a way to give users feedback because it's really confusing when you submit a job and you do a QStat and you're like, where'd my job go? So if you have that experience, most likely you submitted a job that doesn't fit on the small, medium, or large queues. So just check your parameters. You can go to Google and type in ALCF queue policy, and you can find this page here. Oh, this is a generic one. We want Polaris. Polaris queue policies. And actually, maybe it is on the running. Yep, it's on the running jobs page. And you'll see the definitions for these. So small, medium, large. We talk about how prod is a routing queue, and it routes your jobs to one of these places. And so you can get an idea of what's the minimum and the max, what's the min runtime or the max runtime. As you go to bigger job sizes, you can run for longer times. We are trying to encourage users to go to big job sizes because we're a leadership class facility. It's how we get judged by the DOE, actually. So they want to see, right, if we're buying these big machines, that people are using big portions of them, not running single node jobs all the time. So, okay. There are other details here that you can look at. I try to.
Taylor,
Yep.
could you mention one more time how people can check the status of their job from a different terminal browser?
Right. So, I mean, if you're running you can always open up another terminal and log into Polaris again, right? So you can have multiple terminals that are all logged into Polaris. And so you can run them side by side. Does that make sense? Or were you explicitly talking about when I had an interactive node?
Yes, the interactive node, and you want to see the status of your job, and I guess it's not outputting directly to the terminal, so you don't see it.
What do you mean? I'm not sure. Is there a question in the...
You want to see if your job is still running on the interactive node, but you want to use a different terminal browser to see that.
Okay, I mean, that's more like if you're not familiar with running a terminal to log into machines, I would recommend a different tutorial because that's, I would say, out of the scope here. Like if you're not familiar with with terminal usage, I would recommend doing some Googling for how to use a terminal, how to use multiple terminals. Because that was really just opening another tab in my terminal with a new terminal. So I had two side by side. So that's all that was.
Yeah, and then you just use QStat, which is what I told one of the attendees, but I wanted to double check.
Yeah. I just opened another terminal while the internet active job was open, used QStat from there.
Thank you.
Okay, so let's quickly talk about compilers. So you can certainly build up your own environment. You can use Spec, for instance, to do that, and use all your own tools. But if you want to hit the ground running using what's already there, which is what I recommend, there are these wrappers that Cray HP provides in our environments. And so when I talked about, for instance, these environments here. So right now I have the GNU programming environment loaded. If I use little cc and ask for its version, it's going to say, well, I'm GCC 12.3.0. And that's because this is a Cray wrapper for whatever GCC is part of the environment. And then if I do capital CCC, it's going to say, well, I'm G++ 12.3.0. Now I can swap out GCC via the environment variables by hand if I like. You should be able to see, I would think, maybe not, maybe it's hidden through the wrappers in this case. I guess it is. But I believe if you were to add a different GCC version, if you prepend that to the path in the LD library path, these wrappers will honor that and grab them instead. And the reason you use these wrappers is because there are important things like the fabric library for the high-speed network. There are important things like the Cray or the NVIDIA drivers. There are important things like the MPitch library, right? That is specifically built against the libraries for our high-speed network. So if you download and install MPI yourself and you build it, and you don't know where libfabric is living on the file system, and you try to build that, what you're going to find is it doesn't work. Like MPI fails to cross the nodes, and you only get MPI working on a single node. And that's because it wasn't compiled against the proper libraries to use our fabric. And so what CC, with little cc and big CC, and also FTN, which is the Fortran compiler, what those do for you is it automatically, when you build, it will add those things in for you. It will add the MPI libraries and the fabric libraries so that you don't have to worry about those. Now, if you're a savvy user and you want to control all those things, you should go right ahead. But these are just a quick and easy get started for people who want to just hit the ground running. So let's quickly go through. I have this example that is just C++, no MPI, no CUDA, and it just prints hello world, right? So we're just going to do an example compilation. So with that, actually, I'm going to return to the default because that's probably what most people have loaded right now. I'm going to do module switch programming and do the NVHPC. Okay. So we're going back to, this should be relatively close to what the default is when I log in. And you'll notice when I change that programming environment, so before I was using GNU, so little cc and big cc were using GNU compilers. But now if I do little cc version, you can see it's switched to NVC 23.9. And capital CC is NVC++. So little cc is just standard C. It's a drop-in for GCC or NVC. And capital C is for C++ programming. So it is drop-in for NVC++ or G++. I'm sure this is all getting confusing now. Okay, so clicking the wrong, there we go. It's confusing with that one. So now let's build something. So we have this C++ example. So I'm just going to type this command just as it is. Okay, so that's going to build that this example. Now I can, now of course I can run that example on the login node because it's just C++, doesn't use CUDA or anything. So you can see there it is. Hello world, it works. Let's move on, do something more interesting. And we'll start with this CUDA example. So this is compiling C++ with CUDA on the login node. So here I have some implementation of a matrix multiplication on the GPU and on the CPU. So I have the same implementation, fill some dummy matrices, and then I'm going to run those on the CPU side. I'm going to measure the time, or I run each of them. So on the GPU and the CPU, and I'm going to measure how long it takes. And I'm going to print that time on the screen. And so we can compile that using CC, like capital CC, the exact same way we did before. And I don't have to change my command. And the reason I don't have to change my command, except for the input file name, is because this wrapper is automatically adding all the CUDA pieces for me. And in a moment, we'll see it also adds all the MPI pieces for me. So now, of course, if I had left the GNU environment in place, it would try running this with G++, and that would fail. It would need to, I would then need to control and use the CUDA compiler for this instead explicitly. But since I'm using NVC++, it already knows. Okay, so now I can try to run this, but I don't. Actually, I do wonder about the, yeah. There are CUDA devices on the login nodes, but you're not supposed to be able to use those without submitting a job. But we'll go through the example here, which is now submitting my executable to a queue and watching it execute. So if I go in here, I've already updated this to be set that queue correctly. And of course, I'm using the full path to the executable here. And then I should be able to submit. Okay. You can see that's in the running state. And I guess it either errored or exited. Let's see. Don't see any errors. Good. Okay, so there you see, as we would hope, the GPU time is faster. On the GPU. And so then let's go on to an MPI example. So for MPI, I do this again, but now I have added at the top, I've added the MPI init. I get the world size and the world rank, and I print that to the screen so that we can see that we're actually doing MPI. Okay, and so we'll build that example. And again, I don't need to change anything except for the input file, because CC is going to deal with the NVIDIA. It's going to add in the libraries for me, the MPI libraries. And now we'll submit. So now in this example, I'm going to change this a bit because I want to see more than one node. I want to see that MPI is working, because it's easy to build MPI for one compute node and have it work properly. If you don't get the right drivers, you won't see consistent MPI behavior across multiple nodes. You'll see each node acting independently. So here I'm going to change my select to 2 nodes, so I can run with 2 nodes. And now I'm going to do some trickiness. I'm going to use the fact that PBS creates a file in /temp that has a 1-line list, or a list of all the nodes that my job has access to. So these are the node names, 1 per line. So I'm going to use WC to count the number of lines in this file, and I'm going to set that to the number of nodes that I have. So that's just a quick and easy way to get the number of nodes that you have. And then I know that I have 4 GPUs per node. And then I'm going to calculate the total number of ranks, just multiplying those together. So then I have my total number of ranks, the number of ranks per node, which is just equal to the number of GPUs per node. I'm going to tell MPI where to find this PBS node file, because MPI needs to know the host names of all the nodes that I have access to. And then I'm going to specify my executable. And this executable could be anything, right? I mean, if you're familiar with MPI, this can be another bash script, or Python, or whatever, anything that is MPI enabled. Okay, so let's go back here and we'll submit that. First, I want to make sure that my script is set correctly. Set this back to LCF training. No, that wasn't right. I gotta come back here. Grab the queue name. Okay, is everything else here correct? Looks like it. So then I can submit that. Everybody following along? Oh, violates queue. Oh, that's right. Because in this, we set this queue up so that everybody could only run one. Okay, so we'll be stuck with one node for but I encourage you to test this on the debug queue. Okay. You can see my job is queued. Still queued. Changes to running. And it's done. Okay, so there we go. We can see from the bash script where I printed out those environment variables so that we could double check our settings. Got one node with 4 ranks and 4 ranks per node. And so here you can see in the program, each one running on the GPU and the CPU, and we have different ranks. Okay. And I think that's the end for this. And then we go into profiling, which will bring us to the next section. Okay, I'm going to stop sharing.
Thanks, Taylor.
Okay, so do you guys see my screen?
Yes.
Okay. Okay, so yeah, thanks, Taylor. So Taylor talked about how to access the system, submit the job, and how to build your code with simple example, right? So next 15 or 20 minutes, I'm gonna talk about some simple example about how to profile your code. So let's assume your code is working on our system. So there are several choices on our system on Polaris, but in this webinar, we're going to talk about the NVIDIA tools. So NVIDIA provides Nsight tools, and it has multiple tools under the hood. So first thing is NVIDIA Nsight System. So you can use this tool as a system-wide performance measurement, right? So it has very little overhead. And you can also find out, you can run it with the Nsight system, and then you can see what kind of performance your code is doing on our system. And you can also find out what is performance bottleneck. For example, in general, one or two kernels may spend a lot of time on the job, right? So you may identify what is bottleneck. So once you find out some kernel of interest or some bottleneck, you may want to go deeper with the performance tools, right? So in that case, you can use NVIDIA Nsight Compute, so which is an interactive kernel profiler for CUDA application, and they provide a lot of the hardware performance metrics for the kernels. So it has a higher overhead than Nsight system, but this is a really good tool to go deeper to investigate what's going on in your kernel, right? So on Polaris, both of tools are available from your the Pro Environment module, and this section, the goal is we wanna show how to run the NVIDIA profilers on Polaris. And you may need to install the NVIDIA profiler on your local system as a post processor, and then we will see what kind of result we can get from Polaris. So if you go down, as you can see here, you can see the step-by-step guide. So, as Taylor showed, you need to, we will use interactive job mode for testing. So qsub-i and then submit the job. Once the interactive job started, you need to use a soft module file and then load the CUDA toolkit standalone. So you don't have to do that, but the CUDA toolkit standalone 12.5 it provide the latest CUDA toolkit, so you can try it out. And then if you do the module list, you can see this type of the modules. So all of them are system default, and then I added the CUDA toolkit standalone here, right? Since we are using the latest one on Polaris, if you do the NSYS version, you can see NSYS version is 24.2 version. The NC version is also for the 24.2 version, right? So this is the version, and then the instruction for NSYS is pretty simple because you just need to type the NSYS profile and -o, and this is alpha file name for your the performance data, and then dash the stat true, and then you just need to add your application here and some command line argument for your application, right? So you just need to remember this part, adding before your application executable. So after running the Nsight system, let's assume you find out a couple of 1 or 2 kernels of interest, right? And then you may want to go deeper with those kernels. So in that case, you can use Nsight Compute here. So for the Nsight Compute, you can just use NCU -set detail, and then -k and the kernel name. So I will show you some example how to handle that, but basically this is a basic structure. And then you need to specify what is your alpha file name for the NCU measurement, and then just put your command line for your application. So if you don't put the -o, it will show you some standard output, which is somewhat similar user interface like NVProp. A while ago, it was very popular, but now people start using Nsight System now and compute. And we recommend to see the data in the GUI environment because NVIDIA GUI environment is pretty intuitive and handy. But for some reason, you may want to see, I may want to glance what happened on the performance profiling, right? In that case, you may see the CLI interface. So NSYS stat and then the alpha file name. I will show you what happened with the application in the standard output. And for NCU, you can just put NCU-I and then alpha file name, and you can see the standard output, right? But again, our recommendation is use GUI interface. First of all, you need to install the Nsight System, Nsight Compute, the current version on your system, okay? So if you go to this Nsight System link, you can see, you can go to Nsight System link from the NVIDIA, and then you can see the download here, right? So if you go to download, it provides, so right now the 24.4 version is available, and it also provides for different OS. So in my case, I'm using Mac OS. I just download this Mac OS and install it, and you can do that, right? And Nsight Compute, you can go to this link as well here, and it shows some overview of the Nsight System, Nsight Compute. And if you scroll down to the bottom, you can see download now here, right? So if you go to download now here, it also provide, yeah, so currently the version shared is 24.2 version, which is the same version as our system. And it shows Windows version, Linux version, Mac OS version, and ARM server version, right? So you can choose whatever for your local system, okay? So you need to install these 2 tools on your local system. And then once you run the NCU and NSYS on our system, you will probably see some files ending with nsys.-rep and SQLite. These 2 files are the alpha file from the Nsight system. So you need to download them to your local system and open it up with this client version. For NCU result, you can find out the files ending with NCU-REP, which is the NCU result file. Again, download to your local system and open it up with Nsight Compute on your local client version, okay? But again, this is very, very introductory the example. So NCU and NSYS has a lot of features. So for more detail, you just type the NSYS-help. You'll see a lot of the features you can try it out, okay? And NCU as well. So yeah, so let's try some hands-on examples. So in this example, I just want to use a relatively simple benchmark, but not really simple. So we can see multiple kernels in the application and also multiple instance in the application. So I want to see how the Nsight system, Nsight Compute handle that situation, okay? So at the bottom, you can see all the example, but let's follow one by one. So in this terminal, I already got a notes, and the default module is here, right? So as I mentioned, module use soft module files, and then module load CUDA toolkit standalone 20.25.5.0. And in addition, for this example, I want to load the spec PE base and CMake because my example needs CMake to build that application. So I just load 3 modules, CUDA toolkit standalone for the latest NC and NCU, and also spec PE base and CMake for the example. Okay, now if I see the module, you can see we have additional module here, CUDA toolkit standalone and the spec and CMake file, right? And then let's go to the ALCF example and Polaris example. And in this example folder, we don't have that example, but I just want to git clone this spec, not the Babel stream example, okay? So git clone and then Babel stream example. So if I do that, I will just get the copy of the Babel stream on this folder. And also I clone this one on the project space of the LCF training. You can also copy it from there if you want. So let's go to Babel stream here, and then let's build it. So build is simple, just a CMake with multiple options. So CMake, and then I want to build under build Polaris, and then using CUDA, right? So I just finished the configure. Configuration is done, and then let's just build it with the CMake. So if you go down, CMake build and build Polaris. And you compile the CUDA stream and main the CPP. And then finally, you can see, if you go to build Polaris, you can see the CUDA stream here, right? Now let's try to run it, CUDA stream. So it is basically, stream is basically measuring the memory bandwidth with the multiple kernels, right? So it has a copy, multiplication, add, and triad kernel and dot kernel. And using these simple instructions, it tried to measure what is the memory bandwidth of system, right? So as you can see here, from triad case, the A100 GPU provide a little bit less than 1.4 terabyte per second, which is very, very fast memory bandwidth, right? Okay, so now we just done. This is not relevant to Nsight System or Nsight Compute. This is just to build the example case. And then let's move on to profile for the stream with the Nsight System. So if you go down here, there is one line for the Nsight profiling. So let's try to run it here, okay? So what I did was I just put the Nsight profile and -o, and then I just specify the alpha file name for the Nsight system, and that's just that true, and then the CUDA stream. So let's try to run it. And you will see the same standard output, and then in addition, you will see additional standard output from the Nsight system, right? So here you can see this is the report for the CUDA API, and also if you see the CUDA GPU kernel sum, you can see what kind of kernels are executed here, right? So as you see from the standard output from the CUDA stream, you can see it has add kernel, triad kernel, and the multiplication kernel, dot kernel, and copy kernel, right? And if you see here, there is a column for instance. That means that this kernel executed 100 times. So everything executed 100 times. And you can also see the average runtime of kernel and total time and the percentage of this one, right? So this example is very simple, but let's assume, okay, here the add kernel and triad kernel spend 25% of entire world time. So let's try to see what happened with these corners with the Nsight Compute. So we can do the next step. But before moving on, you can just compare what is the standard output from the application. So you can see here, Triad still shows 1.37 terabyte per second, which is pretty similar to runs without Nsight system, right? So from this comparison, we can see the overhead with Nsight system is negligible. So you don't see any big difference between this measurement and this measurement, right? So from this comparison, we can confirm the Nsight system overhead is pretty low. So you can try for entire application. Okay, so now let's assume we are interested in add kernel and try the kernel, and let's try to get the more data with Nsight Compute. So for that, if you go down, there is another example here. So we can just use this one, NCU. So what I'm doing here is I just put the NCU and dash set the detail because I want to collect some detail data. And then dash K and regex, and I use a triad and add. That means I want to collect any kernel kernels, including triad or add. So I just I don't want to profile any other kernels but triad and add kernels, right? Then I specify the Nsight Compute alpha file name here, and then I just run the CUDA stream. And then if I run it, again, you can see the beginning of head, and then now the standard output is pretty, different from the previous case, right? What happened here is it says profile add kernel and 18 passes, and try add kernel 18 passes, and repeating this one, right? So what it is doing is, in order to collect very detailed hardware performance counter data, Nsight Compute use kernel replay options, which means in order to collect all the corresponding performance counters data, it replay your kernel 18 times. So that means your kernel your entire runtime has pretty high overhead because it actually repeating your kernel execution, right? And in addition, everything is synchronized, and because of that, the overhead is pretty significant. So now, because of this reason, the Nsight Compute, we can say, has very high overhead. So don't try to profile every kernel with Nsight Compute. It will take forever, right? So just look at the overall performance with Nsight System, and then point out the check one or two kernel of interest, and then just profile them. Otherwise, it will take forever, okay? So now it will take some time. Let's look at what kind of information we can get from GUI interface, okay? I already downloaded the Nsight system result to my local client, local system. So once you install the Nsight system, you can see the Nsight system here, right? And then if you open the file here, and I already downloaded to NSYS favorite stream, nsys.rep, right? So you can open it up. And then this is first case, right? So you can see the CPU and GPU. So if you stand it, it is 77% kernel and 23% memory and 25% add kernel. If you can add the plus and plus and plus and see the more kernels here. So as we saw in the standard output, we have add kernel, try kernel, and the multiplication dot and copy kernel, right? And you can see a lot of kernel activity happen here, right? So let's zoom in a little bit here. So zoom in the selection, and also again zoom in the selection. So if you zoom in enough, you can see the void add kernel executed here, and try the executed here, and something like that, right? And if you want to see more tableized the data, you can click the kernels and then show the event view. Then here it shows all the kernels executed, right? So started with the initial init kernel, and then copy, more, add, try it, dot, and repeat it, right? So if you click one of them, for example, the triad kernel, you can see the description here. So when it started, when it ended, and what is the grid size, block size, and and what is memory total size, and then what is the shared memory execution size, right? So this kind of information you can get it, right? So this is the kind of a simple the example how to use the NC GUI. And okay, so Nsight Compute is still running. It's pretty high overhead. So instead of waiting, let's go a little bit more. What kind of information we can get? So if you scroll down, there is some animation here, but also there is some screenshot here. So once you open your Nsight Compute result, you can see some summary and details. So if you go to details, it shows the GPU speed of write throughput. That means basically for the maximum your memory bandwidth versus maximum compute peak, how well your kernels are using those resources, right? And also you can see some compute workload analysis, memory analysis, etc. We can see together later. And if you expand GPU speed of write throughput, you can see this kind of table. So definitely in this kernel, I just showing the triad kernel in this example. Triad kernel is to measure the memory bandwidth, which means it does not have a lot of compute. It has a lot of memory operation, right? Because of that, GPU throughput for the compute is very little. It's around 5 to 6%. The memory throughput is almost close to 90% because we are measuring the memory bandwidth, right? But if you use different kernel, it may have some different situation. And another option you can expand is you can also see the roofline model, which is one of the most popular, most intuitive performance model for users. So in the roofline model, on x-axis you see the estimate intensity, which is power by ratio, and y-axis you have the plot rate, and it has two loop lines. Inclined one represent your peak memory bandwidth, and the horizontal one represent your compute peak. So in this case, you have two horizontal cases, which means the one is for SP, single precision, and another is for the double precision, I guess. And since triad kernel is for the memory measurement, memory bandwidth measurement, so it's pretty close to the memory roofline, right? So which means this kernel working as expected, okay? And if you are a Ninja programmer, you may be very familiar with what is assembly, right? And then you may want to see whether your compiler works as expected or not, right? So in this example, the main instruction is the A is equal to AX, A times B times A times B plus C, right? Which is double precision, the fuse, multiply, add instruction. As you can see here, this kernel has several instructions, but DFMA instruction spend most of cycle, more than 95% of the cycle used, which means, okay, your kernel assembly successfully built by the compiler as you planned, right? So this is kind of the deeper case. So let's go back to the Nsight Compute. Okay, now it's done. And you can see the add and the triad measurement from the standard output is much lower than before, right? Because your application does not know whether your profiler replay your kernel, so it just measure from start to the end, right? Because of that, it report instead of 1.37 terabyte per second, it says 600 megabyte per second, right? Because of this overhead. So from this example, you can see Nsight Compute is very, very high overhead. So just use for the specific kernel, not for entire application. Let me open the Nsight Compute result. I already downloaded to my computer. So this is Nsight Compute local version. And then I can open the file here. So NCU triad.ncu.rep file. If I open it up, you can see this tab. And this is summary. So it shows the add and triad kernel only because you just profile those two kernels. You cannot see the mer or dot or copy kernel here, right? And then let's click one of them. So let's try the triad kernel, ID 9. And if you go to detail, you can see the GPU speed of write and the workload analysis and also the launch statistics, right? So if you expand your GPU speed of write throughput, you can see this table, whether it is compute bound or memory bound, right? And if you want to the roofline, you can go to the GPU throughput rooflines, and you can see this roofline here, right? And if you scroll down, you can also see what is compute workload analysis based on the instruction and the pipeline. Also, the memory workload, it provides the memory hierarchy in the GPU. So it has local compute unit, L1, L2 cache, and the memory. And then it also provides how much data is transferred between this memory hierarchy. And also launch statistics and the occupancy, and also GPU memory workload distribution and some source counter. And if you're familiar with the assembly, you can also go to source. And then as you can see here, this is the source assembly of the triad kernel. As I explained before, DFMA instruction use most of time, 95% time. If you scroll to right, you can also see some register dependency. So this kind of information is available with this very simple instruction, just adding NCU, dash details, and then some additional flag, right? So yeah, please try it out and let us know if you have any questions. So I think I'm done with this profiling section. Is there any question about profiling tools?
Thanks, Jayhawk. I'm wondering if the folks get a chance to try profiling tool. As a note, the reservation will be available until 2 p.m. Central Time, so you can still try out what was discussed.
Okay, so let me stop sharing, and I think Taylor has another part to continue.
Okay. And I see a question that it says, while we're doing profiling, how to include the MPI information.
So you don't need to worry about the NPI information because, as Taylor mentioned, you guys are using the modules for the different components, right? So you already use the proper modules, so you don't need to worry about any LD library paths and etc. Once you build your application with the MPI, and if you run it with the MPI, you just need to add MPI-1 before the NC or NCU, right? And then you can just run it and then collect the data. Okay, Taylor, please take it over.
Okay. So next, I'll talk about Python environments. So again, the assumption is that you know how to use Python. Hopefully you have some basic idea of what Conda is. If not, it's just a Python package management system. And we will cover how to add the pre-built Python environments to your terminal environment and how to use the Conda module, how to use it to create custom environments where you might need to install your own software. So yeah, so we have pre-built Python environments that are installed using Miniconda. And within these, we build from scratch things like TensorFlow, PyTorch, JAX, and MPI for Pi. And of course, we build those things because we need them to use the drivers for our systems so that they will actually do what you expect them to do across many nodes. And you can load these via modules. And again, you have to have this soft module files in your environment. So if I go back to my screen here, I do module avail. Underneath the soft modules area, you'll see a Conda environment. And so we can do module load Conda. Now this adds Conda to the Conda binary to your environment. So now you have a Conda executable, but Python is still not there. And that's because you need to activate. So Conda activates the environment. And in this case, we just call it base, because it's the base environment that we installed. Now, Python will be there too. So now you can run Python. You can see current one is 3.11. We date our installations because the idea is we install them and we build all of these AI-specific modules using the latest version that exists as of that date. And given how quickly these libraries change and change in ways that break the previous releases, we decided it was better to just install everything at once, date it, and then instead of doing in-place upgrades where users might come back a week or two later and they find, oh, we've upgraded from PyTorch version X to version Y, and now their software doesn't work, that instead we'll just do installations periodically. It does take quite a bit of time because debugging the source code compilation instructions for these packages is not always straightforward. So we tend to do it twice a year, every 6 months. It tends to be correlated to our big workshops. So we try to have a new version installed prior to each of our big workshops so that we have the latest and greatest AI libraries available. So like I said, you do that module load, you do that conda activate, and now you've got Python in your environment. The other thing you might be interested in is creating an environment that's built on top of this base. And it's important to be careful when you do this because since all of these libraries that we're building by hand, all these AI libraries depend heavily on CUDA drivers and the toolkit versions and the cuDNN versions and MPI for the distributed nature. There's so much dependency there that it's part of the Conda installation. And you can easily use these tools in a way that breaks that environment so that you're no longer using our libraries that get you the features you want, and then you end up in a situation where for some, where the MPI didn't get built correctly, or the library for the fabric went missing, because anyway. So we have some explicit instructions here on how to use these. So for virtual environments, which is of course usually the lightest weight way to do virtual environments, you need to include this special flag system site packages. And this just makes sure that it builds that virtual environment on top of the various libraries that we have pre-installed in the Conda installation. And so if you use this, you can use virtual environment the way you usually would, and then you can activate it the way you usually would. And so that should just work. And then you can use pip install to install your favorite Python packages. If you would like to install a different version of a package that is already installed in the base Conda environment, you can use this flag ignore installed, and then it will just go ahead and install. Now, I wouldn't recommend doing that with these pre-compiled versions because it will replace them with versions that don't necessarily work well on our system. You can also do, so Conda, being in a package manager and an environment manager, can create derivative environments as well. It is a much more invasive process than virtual env. And that's because it is making a full-fledged copy of our Conda installation into whatever path that you specify. The reasons you might want to do this, it could be that you want to ensure that that this Conda installation lasts for whatever time. We don't often remove Conda packages, although recently we did. So it's not something we usually do, but so that could be a reason. Another reason is you want to significantly alter the base installation packages, and so you want to have a little more control. So you can do that by loading Conda and then using this Conda create clone. And so here you're cloning the base environment, and you'll remember this is the base environment that gets loaded. And then you provide a place where you're going to install that clone. Usually you would want this to be your project space. It's big. It takes up like 11 gigs, and it's a 15 to 20 minute process to complete. Once this is done, you can activate your environment this way. Now, in the future, you just load up Conda and then activate your clone this way. Okay. Any questions there? This is all pretty straightforward. Okay. And so now we'll wrap up with Jupyter Notebooks. This is not a tutorial on Jupyter Notebooks or batch schedulers. This is how do you use Jupyter Notebooks at ALCF. You can go to jupyter.alcf.anl.gov. I encourage you to do that now. You land at this page. There's a user guide, but there's a choice. You can choose which system you're going to log into. And we'll log into Polaris because that's where we have our allocation. Now, I've already logged in today, but it usually asks you for your ALCF username and the password from the Mobile Pass app. And so now I can select my QSub command parameters because we're using this to create a QSub command. Now, of course, why? Okay. I see time. Okay. I was hoping that our reservation would be on here on this list for today. I'm going to try sending a quick message to see if we can get that added quickly to the service. I don't know if that requires probably requires me to at least restart, but so when you're going through this, you choose your queue, which queue you're going to submit to. Usually you're going to be submitting to debug. It's not the sort of thing where you want often to submit to prod. Prod means that you're going to be submitting at least a 10 node job. And I don't know many people who are doing Jupyter Notebooks with 60 GPUs at their disposal. So just keep that in mind. And of course, you have to choose a project. How are you going to charge this time? Because it is submitting a job to the HPC, and you have to have an allocation that has time on it. And so then you choose a number of nodes, how long you want it to run, and then which file systems you need. Then you click the start. So that triggers a QSub command to the system with those parameters that you specified. So now my job is sitting in the queue. Actually, I can go over here. I can run qstat, and I can see my job right there. Jupyter notebooks, or the server that they're running here, has a 5-minute timeout. So if this job doesn't make it through the queue in 5 minutes, the server will delete the job and you're back to square one. We are talking about ways to make that a better system. It's a good question. I don't know if people will have access to Sophia via this interface just yet.
I don't think so. I think you have to request it. So at least for the people on this project, it's not on Sophia, it's only on Polaris at this point.
Okay, Tommy's not replying, so I'm not sure if we'll get our queue added to the server in time. But this is an example of what you should see. So some useful notes. When you first log in, you'll have access to a number of kernels. One will be probably labeled Python 3, which is literally just whatever came on the node with Linux when Linux was installed. You don't want to use that because unless you really don't need any packages, because it just doesn't have anything installed in it. There will be another one on Polaris that is the conda module that we just loaded via the command line, and it has all the stuff that you might want. You know, NumPy, SciPy, HDF5, you know, all the AI libraries and such. If you decide to make your own custom environment that you would like to use in a Jupyter notebook, you can add it to the web interface using this command. And so when you run this command with the environment loaded, right? So you're running this command in the custom with the custom Python environment that you've built. You run this command and give it a kernel name and a display name. Actually, you don't have to do this display name. It'll default to this name. This one is needed. And then it's just going to grab all your path LD library paths, some other information from your environment. And it's going to generate a kernel.json file down in this folder in your home directory. And it'll look like this. For instance, I did this just using the conda module directly. And so this defines the kernel and tells Jupyter how to run it. And so with that, this will show up either as kernel name or as kernel display name if you've given one in the Jupyter. Hey, my Jupyter started, yay. So it will show up here in this list. So you can see this is the one that comes preloaded. This is the Python 3, which is the default one. And then this is an old one that we've since removed that I had created in a previous time. The other thing to note, you will only be able to see your home directory. So my root here is my home directory. So like you can see the ALCF beginner's guide over here. Right. if you would like to have access to other spaces, for instance, those project spaces. Was it in Grand?
Yeah, particularly.
So if you would like access to other spaces outside of your home directory, you can make a symbolic link to those places. So I make a symbolic link to this space here, and I'll call it ALCF training. And so now you can see I have a link here, and it puts me in the ALCF training directory. Now, if I go back here, I'll see it right there. And so now I can have access to all that space there. So that's just something to be aware of. So here I can start a new kernel using that Conda module and, do all the stuff that I would like to do in Python. Right. And I think that is it. And that brings us to the end. Are there any question? Yeah, so you'll get that spawn failed timeout. Let me kill my server. That was one of the other things I guess I should mention is when you exit, be kind and stop your server. Like if I just exit this terminal, well, I exited, so if I just close the terminal, my job will continue because my server stays alive even though my web browser gets closed, because there's no heartbeat or keep alive functionality there. But since I stopped my server and I do my QStat, I have removed my job from the queue. Yeah, so we're here in the user guide. Okay, any other questions? Now, if in the next hour, because we have the reservation until 2, so feel free to play around on those 64 nodes for another 50 minutes. I will see if I can get Tommy to add this reservation to that queue menu on the Jupyter notebook, because the debug queue will be slow, especially if everybody's trying to use it. So if you start up and you try that queue name and you see an R20111010, then you know that's been added and you can try that. So, okay.